Welcome back, ladies and gentlemen. I would like to welcome you to Let's Talk Energy Power On, where today we are in the world of large scale. We are into our second session of the day, which is going to be about the epic battle of the ideal plant architecture. And for this, I would like to welcome not one, but two interview partners I have in this session. Please give a huge round of virtual applause to the head of product management, Central Power Conversion, Carsten Wendt. Hey, Carsten.
Hello.
How are you doing?
Very good, thank you.
Okay. And next to Carsten, we have the platform product manager, Hariam Prarak. See, I practiced so long, I'll try this again. And next to Carsten, we have the platform product manager, Hariram Prabhakaran, also known as Harry. Harry,
Hello.
Great to have you here.
Thanks to have me here.
Okay, so as I said, if you have any questions that you'd like to ask Carsten or Harry, just put them into the interactive tool. And with that, Carsten, I need to ask you, I mean, this title is fantastic. It sticks out, you know, in the entire agenda of yesterday, home and business, and today also large scale. So what's up with this title?
Well, first of all, thank you. It's quite a common question which we got asked over the last years, and I've been with SMA almost 11 years, and 7 years out of that I have been working in application engineering, so sitting together with customers, answering their questions and optimizing their systems. And the general question was always like, what's better, central or string? And like a good lawyer, we always answered with, it depends. So, and that's what we want to discuss today. So there's lots of different aspects which you have to look at, and we are in the good position to have both solutions, so we can be quite neutral in answering that question.
Harry, can you tell us a little bit more about your position right here at SMA?
Yeah, I'm a platform product manager of Peak 3, our string inverter, which has 150 kilowatt, and it has the 1500 volt technology. So I haven't been with SMA for as long as Carsten. Nevertheless, I looked at the topics that are important, and I have come to the same conclusion as Carsten, that the architecture is an important topic that we have to discuss about. The reason is that, you see, what is important for the client? The energy that is delivered to the grid. And it's not about one single equipment. It's about the interplay of all these equipments together that brings the energy to the grid. Therefore, the architecture is absolutely important, and there are important differences and similarities in these architectures, and we have to discuss about that.
So can you explain the string architecture to us in terms that professionals and also non-professionals like me understand it?
Absolutely. If you look at this, now before getting into the slide itself, I want to explain that we are not just talking about string versus central here. Within string, there are two different architectures. Number one is a central string architecture, and number two is a decentral string architecture. Let me just quickly go through the central string architecture here. Let's start at the top of the screen. You see that there are these PV panels, and to the top left, there are 10 PV panels. And these constitute two strings. This is what we mean by strings. And then there are these blue cables, which are DC cables, and they bring the electricity, DC current produced by the direct current produced by the panels to the combiner boxes. And the combiner boxes are these yellow boxes that are sitting close by these panels. And then from there, these are these long DC cables that come to the inverter. And these inverters are these 4 boxes that are sitting under the panels, yeah, and there the direct current gets converted into alternating current, and then that gets sent to the transformer, which is at the very bottom. So the 4 inverters which are there close to the transformer is what makes it a string as well as central architecture. So it has the best of both worlds, so to say. It has the string architecture on the AC side, and the central architecture on the DC side. So this is, and also you see that the communication cables are very short, and they are closer to the grid. And this is the central architecture. To contrast this, just keep this in mind. And if you look at this, this is the decentral string architecture. The PV panels are the same, and the DC cables that bring the DC from the modules are the same, and then they don't go to the combiner boxes. They go to the inverter directly, and those inverters are distributed kilometers across the field. And then they bring the electricity in the form of alternating current in those red cables to the transformer, which is sitting at the bottom of this page. So this is the decentral architecture. It is called a decentral string because the inverters are distributed across the field. So I think, and the communication cables, as you can see, they have to go from outside a long way to reach those inverters. So this is the decentral architecture.
Okay, thank you for that. I'm still with you. I could still follow you, so that's good. Important information here. If you would like to get the slide in full screen, you can always do so. Then you can see the details just a little bit better. So Harry, let me get back to the title: good versus bad. So who is good? Who is bad in this epic battle of castings?
Well, good, bad are very black and white. I like to see a lot of gray. But more on the white, I would say the central string architecture is what is the peak 3 architecture, the one that I explained before. Is the peak 3 architecture. The advantages are as follows. The DC cables bring the electricity to the inverter, and the AC cables are very short. So the losses of the AC cables are nothing. In an oversized DC field, these losses can be compensated on the DC side, but not on the AC side. So when you keep the AC cable short, the energy loss is minimized. On top of that, from the point of view of grid management, as it is closer to the grid, the inverters, modern inverters, our inverters are more of computers. So they react like that to signals from the grid so that it's very snappy and it's within 500 milliseconds. With the decentral architecture, that's not possible. That is, it takes a long time because, as you can see, they are distributed kilometers away from the inverters themselves. And one more point is that sometimes the DC and AC cables mix. And in one case, what happened is the signals jumped from the AC to the DC, and it went into the field, and it got transmitted outside because the modules act as a huge antenna, and the clients started picking up noises in their radios, etc. And people thought they were being made by aliens. So to know more about this, probably we'll discuss about that later. That's the plus and minus. On top of that, I can quickly discuss very clear cost advantages in terms of cabling costs. You see that, as I explained, the DC cables that you see in the middle, right, are 2 runs, one positive and one negative. For the same length, you see that the AC cables onto your right are in red, and they are 4 runs if they have an anti-PID solution. So 3 neutrals and 1 neutral and 3 lives. So this increases the cost a lot. And in one case, I would say a study that we did proved that it's 8 to 10% more expensive than a central architecture. So those are important savings for the clients, I would say.
This was a study you did at the Fraunhofer Institute, right?
No, this is a study that we did ourselves inside. And then I'm going to quickly talk about the MPP, so multiple PowerPoint tracking. In a decentral string architecture, you have multiple MPP. In a central, you have a single MPP. If you look at this graph, what you see in blue is voltage, and what you see in red is current. You see that at 5:30 a.m. in the morning, this is from our real operating plant in Ukraine. It's not the best country for solar resources. Nevertheless, at 5:30 a.m., the voltage goes up and it stays there till a very long time. However, the current fluctuates. And MPP is tracking the voltage and it's not tracking the current. So when the current is wavering, it is wavering because of factors that cannot be controlled by everyone, because of the cloud and because of a shade, so on and so forth. So if the voltage is going to stay there at the same part, the advantages that you gain out of multiple MPPTs are not a lot. There are some advantages, but at a bigger plant level, they are not a lot. some advantage, I would say, out of this multiple MPPT is a marginal increase in yield, but it's so marginal that in an oversized field, it makes not much of a difference. And if this is not sufficient, let me go to an extreme example. And this is what you see here are PV modules mounted on a single-axis tracker, and the one that is at the very bottom is producing 215. That's what you see. It receives the maximum sunlight, and from the backside, so these are bifacial modules. So from the backside also it produces current. It produces 215. The first one produces 215. The one in the middle produces 95. And if you look at this, if you have a string outside, this is as good as the worst module of the string. So it makes no difference to have a multiple MPP tracker. One is as good as anything else. So in a study that we did along with Fraunhofer Institute, we compared the extreme scenario to have a MLPE, so module level power electronics, in all of this versus a huge central inverter, and the difference was like barely 0.4% extra yield coming out of MLPE. If this is the case for MLPE, you can make your own conclusions regarding MPPT.
Okay, I shall be doing that now. We're running out of time slightly, and so Carsten gets the equal time that you have. Very briefly, can you give us 2 examples of the benefit of a decentralized architecture? Very briefly.
As I said to you, because it tracks every string, it might be increasing the yield slightly, and it might. This is number one, and number two, it could avoid mismatches as far as the string length is concerned. However, with good design, it can be avoided as well.
Thank you very much, Harry. Carsten, let's get to you. What about central inverters? What have you got for us?
Yeah, of course, as the name says, it's a central inverter, which is based on a central design. In order to make it simple for our customers, we actually produce turnkey solutions, so which includes the central inverter itself, the medium voltage transformer, and also the switchgear, everything being pre-assembled, pre-tested in a factory, and then shipped to site as a plug-and-play solution, so to actually have even less installation cost compared to many smaller inverters. And yes, so this is also quite an important product for SMA. So we've been working on this for many years as well.
And can you give us an important factor for the system design, please?
So something which has really changed over the last 10 years is the design ratio. So when we started the industry, solar panels were extremely expensive, and usually space was a certain constraint, especially on rooftops. So the design ratio was very moderate. So we had like designs of maybe 100% or 110% DC to AC. But this has changed, especially since we're going to markets where we have rather restrictions on the AC side. So you cannot add additional inverters, but you can potentially add more solar panels, which further increases the design ratio. And this becomes really interesting for the levelized cost of electricity, because especially like here in Germany, not every day is very sunny, so we have very cloudy weather. So over the course of the year, it actually is interesting to oversize, and this typical bell curve becomes more wider, so the shoulders get wider. And this extra yield for the project is beneficial. Till that point, you invest more in, let's say, panels compared to what you get back in additional yield.
Just a quick reminder before you go to the next foil, if you, ladies and gentlemen, would like to see the next slide, which of course you want to see enlarged, you can just go onto full screen here on the product window. And with that, Carsten, here's a couple of points.
So in order to do oversizing, it's obviously some kind of additional stress for the inverter, and this is something you need to take care of as a manufacturer. First of all, you need to have the right number of inputs. So we've seen this on some inverters, that they have very limited sizes of fuses or number of inputs, so that even if you'd like to do oversizing, you're not able to do it because there's not just enough. So what we see that you should at least have roughly about 50% extra inputs to allow some flexibility, but also this oversizing. The other one, which is probably a bit more difficult to see for a customer, is the short circuit rating of the inverter. Imagine you have an internal fault of an inverter, which of course should not happen, but it's still a scenario which we need to take care of. And in that scenario, we need to be able to disconnect the short circuit current of the PV array. Otherwise, this will continue till the sun sets, and we have a burning machine, so which is obviously not good. So the inverter needs to be able to trip the fault current from the PV array. And you usually see that rating on a data sheet. If you don't see it, you should definitely ask for this. As a rule of thumb, you can roughly say you have a 100 amp short circuit rating. This equals to a 100 kilowatt peak of PV array. The last one, which is more difficult to see, but it's very important because that's related to reliability. And I think Jürgen in the first session mentioned that we plan with design reserves. And this is, I think, a very good example to look at it in more detail. So this is the actual power versus voltage curve of a PV array. And usually you would be operating at that orange point. But since you are above the actual inverter rating, there will be some kind of curtailment. And the inverter is not burning this energy inside. It's actually reducing the output of the PV array. So it's actually shifting that operating point towards higher DC voltages. What that means is you actually operate the inverter at higher voltages, which actually reduce the lifetime of internal components like the semiconductors. So what you see on a lot of machines on the market, they have to actually stop operating during that time because they are reducing the lifetime otherwise, or they intentionally do this. So what we did is basically we extended this voltage window so that you can operate even at very high DC voltages, and therefore you do not have to shut down in a sunny day, which is obviously a shame because that's the time when you want to earn some money. The last one, and something Harry highlighted as well, is with the central architecture, we have a very close connection from the inverter to the transformer. And during oversized operation, all the DC losses do not account because you have unlimited or sufficient energy available, so the DC losses do not count, but the AC losses still count. So having a long AC cable from the string inverter to the grid connection is basically pure losses. So you have additional 0.5 to even 1.5% losses, which is obviously less revenue for the plant owner. So therefore, this is, especially with oversizing, quite an important aspect of the architecture.
If you look at the future, do you see any trends that might influence this battle in any way?
At the moment, I see two major trends. I have worked 2 years in Australia, and Australia is a large country, but just 20 million people, and most of the projects are actually located in very remote locations. They have very weak grid connection points. And what we see is that grid requirements are actually increasing over the last years as well. We are seeing this in Europe right now as well. There's the requirements for generators, increasing the requirements for all inverters in Europe at the moment. And what that means is actually it becomes obviously more challenging for a solar power plant to comply with this grid code. And central inverters have a slight advantage here because, first of all, they're 20 times bigger, which means they have a larger budget for the internal computing, for the internal processors. So you can spend some extra money on this. And also, since they are larger, they have a direct Ethernet connection to the plant controller. Because not everything of the grid management is done inside the inverter itself. It also happens at the grid connection point with the plant controller. So you need a fast communication here. So string inverters, on the other side, actually have a smaller computing unit, a smaller processor. And some designs actually have also an indirect connection. They have an additional gateway in between, which adds extra latency. And also their communication can be, for example, power line communication, which has a high latency by itself as well. And then it becomes extremely difficult to comply with it. And the example in Australia was, there was a site I was watching that tried for 3 years to grid access, and they finally failed. So basically, the development of solar project had to stop because of that.
What about storage? That's playing a more and more important part too, no?
That's correct. We see that a lot of people are actually starting to co-locate storage with PV. And in order to do this sufficiently, DC-coupled storage will be a big trend for the future. And this is fairly easy to do with the central inverter. I mean, it's still complicated, and we invest a lot of money into this. But the decentralized architecture has an inherent disadvantage by being distributed in the field. And the major cost part of the battery is actually the balance of systems. So you need air conditioning, fire suppression, all the safety belts in the system are expensive. So you can pay roughly about 100,000 euros for a 40-feet container. If you're trying to cut this into smaller pieces and distribute it, the cost of the safety mechanisms will be higher. So distributing means extra cost for a component which is extremely expensive. And secondly, also, the architecture is difficult with regards to scalability. So you need many DC-DC converters in very small sizes, so they become quite expensive as well. So it's quite an inherent disadvantage of the design. Central string inverters have an advantage because they're at one point, and therefore the large battery is sitting next to it, and you have these economies of scale, like with the central inverter.
Well, thank you so much for answering my questions. Now, of course, it is time to see what questions have reached us in our Q&A coming up next. Okay, ladies and gentlemen, let's find out what questions you have to our two experts here with the string architecture. We're going to pull them up on our screen. Are you ready for anything and everything that might come towards you? So while the questions are coming up, can you give us a definitive battle, how shall we say, battle result so far? Or is it like you said at the beginning, there really is no black and white? Or white?
Carsten?
Yeah, well, there was actually a good scenario. Just a few days ago, last week, a customer actually called me because he registered for this session, and he actually was designing a plant in Spain, and he asked me right away, okay, what's a better solution? I'm running out of time.
I'll let you know now.
So apparently in this case, I recommended the Peak 3 because of what the design looks like and what kind of requirements he had for the project. So we try to be neutral, and we try to, I mean, we have the advantage to have both options. And I'm not trying to just push something because I have no alternative. So whenever the other solution is better, I'm still with Harry then.
That's the thing. So you asked for the verdict. So the verdict is clearly central for sure, both central string and central, so to say. That's what I would say. So SMA as a company, we do have a wealth of experience. So we do approach everything from very objectively. And from what we have seen, central architecture offers more advantages than a decentral one. Rather than saying central versus string, I would rather say central versus decentral. In this, I would say central has more advantages.
Clear winner for Harry here. Okay, let's check out the questions that came in. So, how does SMA mitigate the risks and maximize the profitability for your customers like EPCs, IPPs, or investors? Carsten?
So first of all, the design phase is extremely important. So we are sitting together with the customers. So we have an application engineering team, so helping them to design the right system, especially with central inverters. Some people have some concerns because it's a big machine. They're not familiar with this. They have maybe experience with string inverters. So it's important for us to sit together with them. We also provide extra engineering services on top, such as, for example, grid studies, which are quite complicated, and I guess no one knows the machine better than we do. I hope so, at least. And then, of course, this is the first risk stage, the design. Then, of course, profitability. So we also help with levelized cost of electricity calculations. So I mentioned earlier design ratios, DC, AC, etc. We look at the system so to help them to optimize it. And then, of course, we invest heavily in quality. So we want to make sure that there's a very robust product, which at the end of the day has less downtime and also, of course, less O&M cost for the operator, and therefore then the best possible return of investment.
Absolutely. O&M is also going to be one of our sessions later on in the day. So, next question is how do you design a central inverter system?
Strongly depends on the market. There's not a general rule which you can apply everywhere. We've seen many markets now, especially like desert-like locations where there's more or less unlimited land, but a limited grid connection. So you basically start from the back end. So you start with how much energy am I actually allowed to feed into the network? Let's say this is 100 megawatt. How much additional reactive power do I need to provide? At what temperature, etc. So you really start from the back end, and then you start going forward. Okay, how many inverters is that actually, and how much solar should I connect with regards to DC oversizing? In many cases, you have to start a grid study as well, pretty upfront. Depending on the market, sometimes the project developer is doing it, and not the EPC. And in other markets, you actually start with the land because you have limited space, so you start adding the panels, what fits to the land, and then you add inverters, and then you basically apply for the grid connection with the number of inverters you have.
So there is no standardized procedure, and there is no simple answer.
There's not the ideal project. Maybe the ideal architecture, but not the ideal project.
Absolutely. Okay, so we would like to know next, what's better for storage, string or central inverter?
We had it on the slide. I mean, it really depends on the application. I mean, there's residential and commercial applications for storage. Obviously, there you have string inverters. String inverters provide some nice scalability. But when it comes to response times and grid compliance, especially in storage, this is really key. With a next session about storage in detail. The central inverters have quite an advantage with regards to being very responsiveness and also being grid compliant.
And we would like to know next, what is the disadvantage of multiple MPPs?
Of course, with multiple MPPs, you are increasing the number of components in the inverter. So we did a study. So we said, okay, if we get convinced by this argument that multiple MPP is the right way to go, let's make Peak 3 into a multiple MPP device. And then we looked at it, and then we didn't design one, but we needed 2,900 extra components. So in a study, we found that every 1,000 more components increase the risk by 1%. So by that token, in 20 years' time, you would have to replace 50% of the inverters. So that is a big disadvantage that people are not looking at. On top of that, I would also say that plant monitoring should be on two sides. So if you take a bucket, the top half is the DC and the bottom half is the AC. And if you look at the top half always, and that is MPPT, whether anything is leaking or not, but the bottom half is leaking big time, and nobody is looking at that. And that's one disadvantage of MPP, that is diverting attention from the losses at a plant level, and then they are just focusing on the DC side.
Okay, thank you for answering that question, Harry. Next question. You mentioned before the choice is not black and white. Could you please give an example where the distributed architecture is more beneficial compared to the centralized one? What is special in the given conditions?
As I said to you, if there is a plant which has a layout, very complicated layout. Normally, the layout, if for a large-scale plant, the layout is okay, and you can design the plant to avoid these problems. However, if there is a plant with a very complicated layout, and there are different string lengths, and this is a mismatch. And in this case, of course, a decentralized architecture might have some advantages over a centralized. But again, as I said, with a proper design of this plant, it could be made, apple to apples, it could be compared.
Okay. We have 45 seconds for the last question. What is the SMA solution to minimize the downtime of central inverters when component fails in the inverter means losing a lot of revenue? Of course.
That's a fair point, and probably one of the major criticism around central inverters. There's pros and cons with having less units. So one is obviously when one fails, there's more energy loss. At the same time, you have less service actions, because more units means also more service tickets, more actions to go to site. So it's a bit of comparison of yield or availability versus labor cost. And the other one is we are heavily investing in also predictive maintenance and also empowering the customer to be able to rectify the problem themselves. So we have a virtual support app or predictive maintenance, which help them to do this by themselves.
The virtual support app is a great segue. That's also one of the sessions we will be having later on today. It's also a really good one, so be sure to check it out. And with that, gentlemen, our time is unfortunately up already. Harry, Carsten, thank you so much for answering all of my questions, and of course also all the questions of our viewers out there. Stay tuned right here at Let's Talk Energy. Power on.